Well, for all you guys that had me as a freshman, welcome back to the Cave of Science. And if you hadn't had me before, welcome to the Cave of Science. Well, we're starting Unit 3, and really at this point, I think we're getting into a little bit more of the chemistry of things. So we're going to look today at energy bar graphs, or how to represent the role of energy in physical changes. And we're going to use these energy bar graphs. So the first example we're going to do is look at a cup of hot coffee as it cools. And pretty obvious, the energy of the coffee is going to flow into the surroundings. So first of all, we got to determine what is in the system. And the system in these energy bar graphs is typically what's in the circle. And today in this example, we're looking at a cup of coffee. Everything else makes up the surroundings. So our cup of coffee is the system. So we want to start with coffee and end with coffee, so there are no new chemical bonds being formed or no new chemical bonds being broken. So we can ignore the energy of chemical change right now. So we're going to look at the energy of phase change and do the interaction between particles. The energy stored is really ranked. Solids have less energy than liquids, and liquids have less energy than gases. So we need to somehow represent these on the bar graphs themselves. Probably the easiest thing to do is say solids equal 1 bar, liquids equal 2 bars, and then gases equal 4 bars. And again, solids have the less amount of energy, liquids more, and then gases a lot more. So if we're going to say we got liquid to liquid here, because the coffee isn't changing phases, all it is doing is changing temperature. And we're going to say we have 2 bars at the initial part, and then we have 2 bars after. Again, liquid to liquid. So we're not changing the phase of the coffee at all. Arbitrarily, we're going to use 4 bars for hot coffee and 2 bars for room temperature. Could you use 3 and 1? Yeah. But really, make sure when you do these things, you're consistent whatever values you use. So we're going to say our hot coffee has 4 bars. And we're going to say our room temperature coffee has 2 bars. And again, we're talking about the system or the cup of coffee here. So we have no chemical change. Really, the phase change remains constant. We're saying it's 2 bars. So the initial is 2 bars. The final is 2 bars. But the energy, or the thermal energy, or the heat of the cup of coffee itself has decreased. And we said at the beginning, for the initial, we're going to use 4 bars. And then for the final, when it's cooled, 2 bars. So actually what happened with the thermal energy of the coffee, it decreased 2 bars. And we can show this as an arrow going out of the coffee into the surroundings. And that surroundings is referred to as Q. So we can show 2 bars leaving the cup of coffee going into the surroundings. So we started arbitrarily. We said, okay, the hot coffee is 4 bars. It cools. We're going to call it down to 2 bars. And our energy of phase change, seeing we didn't have any phase change, remains at 2 and 2. So we have a loss of 2 bars of energy. Well, let's try a tray of ice cubes. And it's -8 degrees Celsius. Placed on the counter, it becomes water at room temperature. What do we know about what's happening to the ice cubes? The system itself is the tray of ice cubes. Solid water turns into liquid water, so there's no chemical change here. H2O is still H2O. We are changing the phase. And we know if we go from solid to liquid, the energy of that phase increases. The liquid phase of water has more energy than the solid phase of water. And if we are melting the ice, so to speak, we know the thermal temperature also increases. Now we've got to go ahead and put these changes on a bar graph. All right, so let's look at, whoops, excuse me. Let's look at our phase change. And we're saying a solid, and we're saying it goes to the liquid. And again, solids are 1 bars, liquids are 2. The energy, the system, is the ice tray or the ice itself. Now, we're saying that we're below 0. So we need to show this as below that first line. And then we can generally use 2 bars for room temperature. Again, that might be a nice thing to put in your notes. So we're going to say we've got 2 bars. So we can show that we went from, the thermal energy went from less than 1 bar to 2 bars, and the phase change energy went from 1 bar to 2 bars. So now we can look at the energy flow. Well, if we add the bars together here, we have 1.5 bars. Here we've got 2 and 2 is 4. So energy from the surroundings flowed into the ice tray. So the ice tray gained 2.5 bars of energy. And again, this is somewhat arbitrarily how you want to label these, but I probably would use what has been suggested. So that's an energy flow system. I'm going to be working on some of those in class also.